Hello everyone, so in this video what I'm going to do is I'm going to show you a very special quality that the work done by a force presents, especially in this case by an electric force. So we know that the definition of the work done from the work energy theorem is just the change in energy, right? So energy final minus energy initial equals the work done. Now, but let's take a look at this specific case over here. We have 2-point charges, right? We have one with 1 coulomb and the other one with -1 coulomb. So that means that they're going to have an attractive force, right? So they're going to come together if they're at rest, right? Now, for this specific scenario, suppose that this charge is at the origin and it is fixed, and this one, it is at the point 1, 0. And so what we want to do is we're going to take this charge and we're going to move it, to this point. It doesn't matter which path we take, but for the purposes of this video, I chose 2 paths. So I chose a straight path, right? So the linear function, y equals x minus 1 represents this path. And the curved path, which will be x squared minus 2x plus 1. And I will show you, that it does not matter which path the point charge takes. So the work will always be the same because it is a conservative force. So it is path independent. So I'm going to show you, that this work done by the electric force is path independent. So let's take a look at several qualities over here regarding the electric force due to these 2-point charges. So we're going to find the electric force on this charge due to this charge, and as we can see, suppose that the charge is at this point, right? So that the blue charge is at this point. So we know that the distance between them is r. And so if we break this down, into the x and y coordinates, it's just an arbitrary distance of x and an arbitrary distance of y. Now, but we have to take a look at this. If we're moving away from the positive charge, even though this is a negative charge, and it's an attractive force, so you're going against, the direction of the force, which means that the work will be negative. So in this case, the work done will be negative, right? So it will be the negative of the change in energy. All right, so first of all, let's calculate the work done using the work energy theorem, and then I'm going to prove it to you using the definition of work, as an integral of force. So now, the final energy, can be described as, negative of kq1 times q2 divided by r final, right? Minus times minus is plus, so it's plus kq1 q2 divided by r0. Now, how do we find our final? Where r final is this distance over here, right? So it's this distance from here to here. And as we can see, it's just going to be the square root of 4 plus 1, which is the square root of 5, right? Using the Pythagorean theorem or the distance formula. Now, r naught is going to be equal to, this distance over here. So this is the initial, energy, and this is the final energy. The initial energy has a distance of 1, final energy has a distance of root 5. Very nice. So we can substitute our values. We know that Q1 is -1 and Q2 is 1 coulombs. That's a lot of charge, by the way. But let's see what we get. So we're going to get -1 times -1 is positive 1. So that's k over our final, which we found to be root 5. And then we're going to have minus k over 1. Now we find the common denominator. We're going to find the answer to be 1 minus root 5 over root 5 times k. In other words, 1 minus root 5 over root 5 times 9 times 10 to the power of 9, And the units for work, of course, will be in joules. So now I'm going to go ahead and prove to you that the work done by the electric force is a conservative. It is non-path dependent, which means that the force is conservative, right? So first of all, let's take a look at this path, right? The straight path that it takes. In order to find the work done, we can use the original definition of work, right? The general definition, which is just going to be the integral of the electric force from one point to the other, right? So the integral of the electric force, that dr, from one point to another. So in this case, we are trying to integrate from here to here. But remember that the work done is negative, right? Because we're moving away from the attractive force, right? Good. Now let's define what the electric force is. When we know that from Coulomb's law, that's going to be K Q1 Q2 divided by R squared, right? R hat. And if we find the magnitude of the electric force, well, that's just going to be K Q1 Q2 over R squared. Now over here, let's take advantage of the geometry. R squared is x squared plus y squared. Okay, so we could rewrite this, okay, as negative integral from a to b. We're still not defining the limits, right, of the electric force, Q1, Q2, okay, so that will be K times Q1, which is 1, and Q2 is negative 1, so it will be negative of K divided by, excuse me, R squared. But in this case, R squared is what? Is x squared plus y squared, right? But I'm just gonna rewrite this later, dr, okay. Now, as you can see, the negatives cancel out, so that will become positive. And we can rewrite this as something, okay, as an integral in terms of either y or x, right? So let's choose per se, right, that we're going to integrate in terms of x. But in order to do that, okay, we have to rewrite this entire expression in terms of x. So r equals something in terms of x. We know that we're integrating along this straight path, and that's defined by the function y equals x minus 1. So all we have to do is solve for y over here, right? Solve for r, I mean. So that means that r is equal to the square root of x squared plus y squared, and y is just x minus 1. And that's going to be squared. Okay? And we also have to find what dr is, right? So if we know r, we know r squared, and we also know dr. So if we implicitly differentiate this over here, we get 2x dx, right? So if we implicitly differentiate this, you get 2x dx plus 2y dy equals to 2r dr. The 2's cancel out, and we're left with x dx plus y dy equals r dr. And we solve for dr. So dr is x dx plus y dy divided by r. And we know what r is, right? Now, we have to find this in terms of x only, right? So, excuse me, y is going to be x minus 1, and dy is the derivative of the function, which is just dx, right? So in this case, will be equal to x, and then we're going to factor, okay, dx, so we're going to bring it out, and we're going to have x plus x minus 1, right, the function, times dx. All of that divided by r, and we found that that is the square root of x squared plus x minus 1 squared. Okay, so that is dr. So we could go ahead and plug this into the integral. X plus x is 2x, so this becomes 2x minus 1 dx over that. And we just have to, okay, put it in, and then we know r squared already. So this can be rewritten as integral from a to b. And now that we have defined our integral in terms of x, our limits also have to be, okay, also have to be in terms of x. So it's going to be something like this. It's going to be from 1 to 2, right? We're going to integrate from 1 to 2 because the x coordinates, okay, are 1 and 2. So integral from 1 to 2, and then we can bring the k outside since it's a constant, right, of dr, and dr is this. Dr is 2x minus 1 dx, okay, divided by the square root of x squared plus x minus 1 squared, so that's going to be like that. And don't forget to divide by r squared, which is in this case is x squared plus, okay, x minus 1 squared. And if you bring this together, okay, you're going to have something like this. So we know that the work done by the electric force is equal to k times integral from 1 to 2 of 2x minus 1 dx divided by x squared plus x minus 1 squared to the power of 3/2. Okay, now pay close attention to what's going to happen next. You can take advantage of a few things here. So how about we just, okay, expand this denominator and see what happens. Okay, if we expand the denominator, we're going to get the integral, okay, k times the integral from 1 to 2 of 2x minus 1 dx. All of that divided by x squared plus x squared, right? And then we're going to have minus 2ab, which is minus 2x plus 1 to the 3 halves. X squared plus x squared is 2x squared. So we have that the work done by the electric force is k times integral from 1 to 2 of 2x minus 1 dx divided by 2x squared minus 2x plus 1, all of that to the power of 3 halves. Now, pay close attention to the denominator and the numerator, okay? Very, very convenient, right? We have a very convenient relationship between the denominator and the numerator. In this case, if you take the derivative of the denominator, so if you let u equals to 2x squared, right, minus 2x, right, plus 1, you know that du will be 4x minus 2 dx. And look at that, we can factor out a 2 from that, so that means that du is just 2 times x minus 1 times 2x minus 1 dx. We divide by 2, and we get that du over 2 equals 2x minus 1 dx. And we have 2x minus 1 dx right over here. So we can substitute this du over 2 in here and set this equal to u. And we have the work done by the electric force to be equal to k times the integral from 1 to 2 at x, right, defined at x, in the x world. So we have to substitute x into this u function. So let's try 1. 1 squared is 1, times 2 is 2. 2 minus 2 times 1 is 0, so we have 1. Now let's try 2. 2 squared is 4, 4 times 2 is 8. 8 minus 2 times 2 is going to be 4, right? So that's going to be 4 plus 1, which is 5. So from 1 to 5. Integral from 1 to 5 defined at u, right? U equals 5, and u equals 1. Of du divided by 2, so let's bring the 2 outside, right? Because we have du over 2 over here, divided by u to the power of 3 halves. And the integral of 1 over 3 halves is just going to be, okay, this is going to be k over 2, okay, times the integral of this, which will be u to the power of negative 1 half, or essentially 1 over u to the power of 1 half from 1 to 5. And don't forget to divide by a half, by a negative, excuse me, by a 1 half, which in this case, okay, will make this expression, okay, it will make this expression negative k times that, right? So eventually we're going to evaluate this over here. So we have negative k times 1 over the square root of 5 minus 1 over the square root of 1, which is 1. So we say that this is negative k times 1 minus root 5 over root 5. Then we just distribute the negative. So we have that the work done by the electric force is root 5 minus 1 over root 5 times k. Okay, so basically it is this exactly the same as this. It's just that this is negative, right, over here, because we said that it was negative work done. Oh, so it was my mistake over here, because it is not necessary to put the negative in here, since the integral itself defines, okay, that this is going to be negative work. So, you know, if we don't get rid of the negative, you get a negative over here. Negative times negative is positive. So it will be negative root 5 plus 1 over root 5 times k. Okay, which is exactly the same result over here, and this is in joules. Very nice. Now we found that this work done by the electric force through the straight path, okay, is equal to, okay, the work done using the work energy theorem. Now I'm going to show you that this is the same in the case that the particle is moved along a straight path, like this function, x squared minus 2x plus 1. So we're going to do the integral in the same fashion. All right, so now we have found that, okay, the work done due to the work energy theorem is equal to the work done by the integral along the straight path. Okay, so now I'm going to show you that it is also equal to the work done, okay, shown as the integral of force along this curved path, right? So what we do is it's pretty much the same process. The only thing is just, you know, it's a quadratic function, right? So we have to take care of that. Now we do the same process over here. We want to integrate this in terms of x, right? So it's going to be the integral from 1 to 2, right? Of whatever the r is and whatever r squared is. Now we know that in this case, y equals x squared minus 2x plus 1. And so x squared plus y squared is equal to r squared, according to the Pythagorean theorem over here, since this is a 90-degree angle. And so the electric force is kq1 times q2 divided by r squared, the magnitude of the force, right? And we're going to do the same process. So over here, if we want to find dr, right, we want to substitute dr in there. We have 2x dx plus 2y dy equals to 2r dr. So dr equals to, okay, x dx plus y dy divided by r, which in this case is the square root of x squared plus y squared. And in this case, we have to find y dy. So y is just x squared minus 2x plus 1, right? And if you think about it, if you factor this, you're going to get x minus 1 squared. So we're better off factoring this, okay, into a perfect squared. So we know that, okay, x dx, this is equal to x dx plus, okay, plus x minus 1 squared, and then dy is just the derivative of this, which essentially is 2, okay, using the chain rule, x minus 1. And look at that, they're the same power. So we can bring it together, and it's going to be to the power of 3. And don't forget the x. Now, over here we have the square root of x squared plus y squared, which is x minus 1 squared, which is x minus 1 to the power of 4. Okay? So essentially, we have something like this. Let me write it over here. We have that dr is equal to, okay, we factor out the x, so we have x plus x minus 1 to the power of 3 dx, right? Divided by the square root of x squared plus x minus 1 to the power of 4, okay? Very nice. Now, we want to know what r squared is. We know that this is x squared plus y squared, and we can already plug that into our integral. So let me erase this over here. So we know that the work done, okay, by the electric force along this curved path, right, this quadratic path, is going to be equal to the integral from 1 to 2, okay, times k, of dr, which in this case is going to be x plus x to minus 1 to the third power dx. So it will be x plus x minus 1 to the third power dx. All of that divided by this multiplied by r squared. So it's basically this to the power of 3 halves. See the pattern here? It's just like the linear factor. Okay, so now let's take a look at the integral itself. It looks complicated and messy, but it's actually very convenient. If we compare the denominator and the numerator, okay, if we set u equal to x squared plus x minus 1 to the power of 4, you will see that du is going to be a factor of this. So let's do that. So let u, okay, equals to x squared plus x minus 1 to the power of 4, right? So that du is equal to 2x plus 4 times x minus 1 to the power of 3 dx. We can factor out a 2, so that means that du is just 2 times x plus 2 x minus 1 to the power of 3 dx. If we divide by 2, well, we have that du over 2 is equal to that. And look at that. That's basically the denominator, I mean the numerator over here. And yeah, there's supposed to be a 2 in here. I missed that. Okay. So It's exactly the same as the numerator over here. So we can substitute this by du over 2. So the work done by the electric force, right, is equal to k over 2 integral from, okay, 1 to 5, right? We substitute that in there. We're going to see that it's basically 5. Look, 1 plus 1 minus 1. So, and then we substitute 2, it's 2 squared plus 1, right? That's going to be 5. So integral from 1 to 5 of du over u to the 3/2, and it's basically the same integral. It doesn't matter which curve you do, it will always end up being an integral of this sort. So you're going to have that that's equal to negative k, okay, times u to the power of negative 1/2 from 1 to 5, which is basically negative k, okay, times 1 over 5, 1 over the root 5 minus 1, which is basically root 5 minus 1 over root 5 multiplied by k, joules. And this is going to be the work done, okay, due to a curved path. So we found that the work done by the electric force, okay, is non-path dependent, which means that the electric force is a conservative force indeed, and we have shown it using 2 different cases. All right, so thanks for watching. I'll see you next time, and keep it up. All right, now I'm gonna do the review for calc.